Hello, my name is Iordachescu. I belong to Material Science Department from the Civil Engineering School of Polytechnic University of Madrid, Spain. And in this first virtual European Conference of Fracture, my presentation is about the failure causes of the bridge tie-down cables after 30 years of service. In the introductory part of the presentation, I will briefly introduce the constructive detail of the bridge and the failure description. Then I'll follow by presenting the main research results under the following headings: microstructure, surface condition and mechanical characteristics of the strands wires after 30 years of service, the effect of surface damage on stress corrosion resistance of strand wires, and the subsequent macro and micro mechanism of failure. Lastly, I will end up with the corresponding conclusions regarding the root cause of strand failure. The cable-stayed bridge in which the failure of two tie-down cables was detected after 30 years of service crosses a river in a heavily populated urban area in southern Spain, and it basically consists of a continuous reinforced concrete girder supported by inclined stay cables attached to the towers, two porticoed pylons, and other four load-bearing porticoed piers. In this design, the tie-down cables assure the girder vertical anchoring at the pier's base. The cables are bundles of 12 parallel 7-wire stressed strands mounted inside the piers. After 30 years of service, the rupture of two strands occurred at their lower ends in the anchoring head's proximity. The site inspection revealed that parts of about 0.5 meters at the strand's lower ends, starting from the exit of the anchorage system, were unprotected by the polyethylene sheet. The error attributed to the mounting of the anchorage system remained undetected over time. More than that, this critical area was covered with remnants of decaying dead leaves, birds, and rodents that overlapped to the ambient aggressivity. The pictures taken on site illustrate the pier interior and a detail of one of the tie-down cable's end before its rehabilitation. The samples supplied for the analysis of the service failure and pertinent laboratory tests were strand sections, polyethylene sheeted of 3 meters length, having at one of the ends the illustrated rupture details. Close to the fracture zone, at naked eye can be observed that some of the fractured wires still retain part of their original zinc-coated protection. Considering all the above-mentioned facts, my research group was in charge to determine the failure cause and the corresponding micro mechanism that triggered the strand's collapse in service. The microstructural analysis of the broken strand steel was made on metallographic samples extracted from the strand's end protected by the polyethylene sheet. The wire's microstructure in longitudinal direction consists in axially oriented fine perlite colonies. In contrast, in transverse direction, the perlite colonies are randomly oriented and the cementite lamellas are considerably smaller in length, or when larger, have a curled form. These differences in the microstructure induced by cold drawing are indicators of mechanical anisotropy, particularly of fracture resistance, that determines the failure mechanism of this wire steel. The surface analysis of the wires in areas protected by the polyethylene sheet shows that they still preserve the zinc coating generated by galvanizing as consumable barrier against pitting corrosion. According to Figure 2, which presents the results of the EDX analysis acquired on a wire sample cut in transverse direction, the zinc layer of about 60 microns thick and despite its porosity continues to protect the steel in the sheeted strands. The situation changes drastically in the unprotected areas in the proximity of strands failure. Figure 3b shows the main differences in the zinc layer appearance on the wire surface, namely in the outer zone of the strand and in the contact with other wires. The first is of rough appearance due to both the galvanizing process and the oxidation and formation of porosities by zinc dissolutions up to the corrosion pits formation, while the second is smoother with transverse microcracks as a result of the combined action of the wire's contact, the applied tensile load, and the environment aggressivity. Figure 3c shows a higher damage level in the zinc coating up to its fully dissolution in the strand wire outer surface, together with the iron oxides formation in the unprotected regions of the wire steel. The mechanical properties of the wires after 30 years of service were obtained by tensile testing undamaged wire samples of 235 mm length. The interpretation of this test requires taking into account, in case of peripheral wires, their braiding-induced deformation at strand forming, as well as the influence of the non-simultaneous breaking in service and the subsequent differences in strain hardening. The maximum stress of all tested samples is quite similar, of order of 1860 megapascals, and offers the certainty of considering it the tensile strength of steel wires, since it is reached by plastic instability when the specimen's curvature has vanished and the stress state in the wire's cross sections is uniform. The elastic modulus of the cold-drawn eutectoid steel from which the pre-stressing strands are made of 205 gigapascal is compatible with the unloading line slopes recorded during testing. In contrast, the elastic load slopes are appreciably lower, of order of 150 gigapascals, excepting that of the central wire of 200 gigapascal. The peripheral wires bending during testing explains their higher deformability. The percentage elongation under maximum load exceeds, in all cases, 3.5% required by the standards, but its dispersion suggests that two of the specimens have lost part of their ductility before testing by previous plastic deformation and strain hardening during the service failure. Lastly, the table shows the mechanical properties of the tested wires. These exceed the minimum values required by the current regulation in force despite the service time. In this work, 3 wire samples extracted from the broken strand of one of the bridge piles have been stress corrosion tested in FIP environment. 2 of them came from peripheral wires of the strand sections, respectively protected and unprotected by the polyethylene sheet, and the third an unprotected central wire. Thus, the last two wire samples had been permanently subjected to the pile's interior environment, but the central wire sample have had the additional protection offered by the other 6 peripheral wires of the strand. Figures B, C, and D show the test results as load time dependency. The curve in figure A has been added as a reference and corresponds to a simple tension test. The stress corrosion under constant load tests illustrated in figures B and C were interrupted when they far exceeded the minimum required surviving time, but the wire specimens were subsequently subjected to constant extension rate tensile testing until failure in the same environment. As illustrated in figure C, the central wire, although exposed to the environment action, wasn't significantly altered in the 30 years of service, its stress corrosion resistance being comparable to that of protected wire given in figure B. In contrast, the peripheral wire from the unprotected strand section barely survives 0.5 hours in the FIP solution when loaded to 80% of its resistant capacity. This poor resistance to stress corrosion cracking was attributed to the existence of previous service damage which favored its rapid rupture by hydrogen uptake during testing. The failures of central and peripheral wires in the constant extension rate tensile testing occurred for loads higher than the 31 kilonewtons used in the stress corrosion constant load test, but less than the wire's resistance capacity of 42 kilonewtons. Their premature failure being a consequence of the induced embrittlement by the FIP environment. Accordingly, the origin of the strand collapse was the environmentally assisted progressive subcritical cracking of the peripheral wires propitiated by the zinc coating direct exposure to the service ambient. The macroscopic images illustrate the fracture similarity of one of the peripheral strand wires broken in service with that of a stress corrosion under constant load tested wire previously damaged in service. Both are non-ductile ruptures. The only difference is given by the distinct oxidation of the fracture surfaces attributed to the exposure time of the first wire to the service environment after breaking. The microscopic images show the secondary cracks found in the longitudinal sections of the wires close to their fracture surfaces. The first was broken in service, the latter in the stress corrosion constant load test. In both cases, these cracking processes were interrupted by the wire's failure in a similar process. The cracking micromechanism consisted in the pop-in rupture in tension of the cementite lamellas and of the ferrite matrix by hydrogen uptake. The only significant difference between the two secondary cracks is due to the time that they have been exposed to the aggressive environment, the service crack faces being covered by corrosion products formed after the wire breaking. The main conclusions of present research are: the lack of sheath protection in the strand sections where the ruptures occurred and their exposition to uncontrolled media points out to a local, environmentally assisted damage and cracking process as the cause of failure. The zinc coating was the only protective barrier of these strand wires, but its prolonged direct contact with the aggressive medium severely and heterogeneously damaged it, that propitiated the stress corrosion cracking of the wire steel. The fracture mechanisms found to produce the wire ruptures in service were also found in the equally exposed wire samples when stress corrosion tested in FIB medium. Thank you very much.